But tonight, what I was going to talk about, this is absolutely bizarre. We talked about before how in the sun's fusion, how protons will join spaces, and when they do this, they'll release a positron and they'll become deuterium, and then of course deuterium mixes, and then it releases a gamma ray, and so on and so forth, until the point where this thing will drop 2 protons. Well, it's the craziest thing, but you can kind of think of a neutron as being both a electron and a proton, right? Because it's got a neutral charge. So these things have a lot of value in terms of that. So like when they decay, they break down, and it just makes total sense. They have to give off an electron and a neutrino to conserve. So like this is how, like, when, because quarks, they have baryon number, and they can flip. They're right-handed and left-handed, and when they change inside protons and neutrons, like with a neutron, when the quarks change, right? This is a trip, but like when the W boson comes out and this thing changes, do you realize where I'm going with that? It's going to have to become a proton, so it's going to have to give something else off. So it will give off an electron and neutrino. But see, I don't have to master all of it to get a good sense of what's going on. See, that's the whole point to these videos, is I'm trying to flesh out a physical picture for people, rather than so much and just know every single detail. Because like I said, there is a lot to quantum mechanics. This could take 20 years to really master. But they have right-handed and left-handed. They have up-down, charm and strange, top and bottom. They have color charge. They have electric charge. They have spin. They have isospin. They have angular momentum. There is a lot of numbers that go into what particles do when they exchange energy. But yeah, isn't that a trip? So that means when you get your fusion and you got enough pressure, you're going to create a weak force reaction, right? Because you've got so much pressure, right, that on the other side of things, now the weak force is going to do its work, okay? And this is going to work way inside the atom, dude, right? And it's a trip because, like, sometimes, depending if you have electric charge or not, like neutrinos, for instance, there's no supposedly right-handed neutrinos or whatever, just left-handed, or it might be vice versa, but there's only one type. And then with particle-antiparticle pairs, you also have that thing where, like, with the W and Z bosons have a spin of 1, right? It's a trip. But they can also, the W can be charged or not. And the Z, the zero boson, is a neutral charge. And so that one is its own antiparticle. Isn't that a trip? But anyways, I hope you liked the video. That was a quick